pay people?
I got a question.
Yeah.
I sent you a message on Canvas, but um, how do we attend your office hours?
Oh, there's a link. I'm probably going to switch up the office hours actually to be just for the Wednesday one. I might move it to Tuesday so it's a little bit off. People who have Monday, Wednesday, Friday classes are having a hard time getting to office hours. And so I'll probably switch the Wednesday one to Tuesday, in part selfishly because people will come to my Wednesday office hours, which is right before class, and then I do class immediately after this one, and then immediately after this class I do another class, and it ends up being this marathonic, whatever the adjective is, version of lecturing all day. It has marathonitude. So I will probably move today's to Tuesday, keep Mondays where it is, but delay it 15 minutes because I'm always late getting to it. But what you do to get there is there's a link in Canvas. If you go to Canvas, and there's a very early announcement, it's like the first or second announcement, and there's a link to the office hours. And so you just click on it. It's in Zoom, and it's just its own little room. You just click on that link, and so you'll see it there somewhere. Very early announcement this semester. Do you see it?
Yeah,
Okay.
yeah, that's
So
so stupid of me. It was right there the whole time.
yeah, but
I
but
was
it's
on the
it's
same announcement too, so
but it's I posted that really early and never went back to it. So I assume
do you
other
mind if I
people had
ask a
that exact
question
same
now,
question. Pardon?
I think other people might have the same question that
Yeah,
I was
so
gonna
I
ask.
think I'll repost that one maybe later tonight or something. I'll post new office hours just because Tuesday people have asked if they can do Tuesday, and Wednesdays are just rough because I get to the end of my second lecture and I just um my ongo just I get fatigued by that time and then my lecture sucks. So I'll repost information about office hours later today.
I do have a quick question though
Yeah.
regarding the lab.
Okay.
Um, I think I finished my tables and all that stuff,
Good.
but I'm looking through the rest of the lab, and we have to do it by variate correlation.
I'll talk
And
about that today.
okay, because I have no idea what we're supposed to be looking for in that.
Okay. I'll talk about that today. And it's the easiest thing.
Okay.
It's way easier than the table. So if you've done table one, the bulk of the work, you just have 5 minutes ahead of you.
Okay, cool.
It's
Thank you.
super easy. Yeah. So if I get to that section, which is going to be 10 minutes into the lecture or something, I don't know where it falls in here, but I do talk about it today. If I get there and I breeze by it without referencing lab, like unmute, hold up, and make sure that I explain that. All right, let me queue up the slides. Okay. So we're going to start talking about regressions. That's lab 2 is regressions. We'll introduce what will be on lab 2, what lab 2 is about. But you still have, so we're here, right, Wednesday, but this Friday, lab 1 is due. Email it to Nathaniel, our graduate assistant, and he told me he was working with some of you already a little bit. Make sure you don't put off the lab until Friday because there may be SPSS problems people have in getting compatibility with their computer, and you'll be able to get it to work out, but there may be a little bit of troubleshooting that you have to work with. Let me get the comment box queued up. Okay, yeah, so there's another question in the comment box about bivariate correlations. I promise we'll talk about that. So just remember the research topic is also coming up very soon, and then exam 2 is October 21st. And the readings, right, if you care to do them, my hunch is nobody's doing them, and that's fine because everything you can be held accountable for is going to appear in the slides, or it's going to be, audibly coming from my mouth. So if you just re-watch these lectures and re-listen and take your notes, you'll get everything. If you want to enter the world of data analytics, I would definitely recommend the book readings. It's a very high-paying, easy-to-get job. If all you have to do is demonstrate that you know how to do it, and everybody's in need of analysts. what we have, again, just a point breakdown, where we are so far, right? There's a countdown. We've already done this, and we have all of these to go. And those are the exact dates that they're due or that they fall on, and right through the final exam. So we have our timing signature of when everything's due. This is just a suggestion that October 12th of when your poster groups should be chosen, but the poster titles are due. That's an actual due date, and you just email it to me. Just send it to me in an email, cjensen1@pacific.edu. None of that u.pacific. And if you send to cjensen at, I have no idea who gets that. Some female, Courtney Jensen probably. And October 26th, that's the executive summary. You're going to put together a poster. It doesn't have to be this comprehensive, right? This was we presented this one in Florida and published it, and so make it good, but it doesn't have to. You don't have to hold yourself to a standard of, if I don't publish this, then I'm going to get a C or something. Just make it as good as you can. And when it comes time to do the posters, sometimes people will try to rely on me to help with either the writing or help with the analyses or the interpretations or something. And there's going to be, a dozen or more posters. But as we go through class, I want you to learn. Nathaniel's available. I'm available as we go through class to learn the labs and learn the analyses and learn interpretations and even how to write. I'm going to do a couple of lectures on writing just to get everybody uh, the pacing a little bit faster of the improvement in the craft of writing. And but when you get to the posters, you're going to be pretty solo. I can be available for brief questions, so can Nathaniel, but the idea is to demonstrate what you've learned this whole time. No more than 4 students per group. And I did post in Canvas, I posted a discussion where it's not like a discussion. It's just where people can say, hey, I have an idea. I'm looking for a couple of group members, or I have no ideas. Will somebody adopt me into your family, into your poster family? Just a place where, like a meeting grounds where people can try to link up, because it's harder to do in a digital format. It's harder to link up with people because you can't just turn to the person sitting next to you and say, hey, be my partner. And so do we email you our groups? You don't need to email me your groups, but there's a question in the sidebar. But when you email me your poster topics, put the groups in that email. So as you send me your actual titles, which can change a little bit as you go, as you get findings, as you analyze and find stuff, your title's going to change a little bit as you go, but thematically the title should stay relatively the same. And let me know what groups are in that as you submit your title. So this just resources online. If you want to go browse publicly accessible data, wonderful. Like this is the internet is a remarkable resource for finding data, whether it's healthdata.gov, again, Berkeley's library. Eastern Michigan University has a bunch of free data sources on their library webpage. Internet sites all over the place, whatever you want to do, if it's FBI stuff, if it's causes of death, if you want to get out of health statistics and look at more marketing or business economic things, there's tons of that stuff. Bureau of Labor Statistics or Airbnb or whatever. This is a really good one. If you go here at this address, this sharing data to advance science, this website, you just find data, you click on that, and then you browse for databases, and there's tons of databases here. And within that same domain, if you go to this HMCA, same thing. We're looking at this health and medical care archive. Tons of data here. I made an account. It's free. It doesn't cost anything to make your little accounts. And then just find data, and you can find whatever: public health, university health, health data in general, behavioral health, health survey, like all of these different domains. And you just pull up these databases, mostly Excel file databases, and you just get to use them, right? So you click on SPSS, or don't do Stata, SAS, R. I mean, these ones, we don't have that. Technically, you do have that software. You have access to that software, but SPSS is what we're using. So these are just different statistical packages. And if you can just get files in SPSS, you open them up and they're ready to go. So you have your research question, you know where to search for it, and then you have your background done. You're going to begin analyses. Some of you have already started analyses. You have SPSS, you're running them, you've made a table one, you're more or less doing the bivariate correlations, and we'll get there. But remember, in SPSS, there's variable view and data view. Variable view is showing the variables and the types of variables they are. So numeric just means things are coded as numbers. So numeric, this is the stuff you analyze. Who cares about these two? Labels, this is just what shows up in your analyses. Labels can be empty, who cares? Values are helpful to assign, where if it's, sex or gender, you code 0 is male, 1 is female. But when you're looking at your results, you don't want to try to remember, oh, as you go from, the zeros are this and ones are this, you want to remember males are this and females are this. So in the outputs, if you code stuff here, then that shows up in a more coherent way in your outputs in this values column. Labels doesn't really matter. This doesn't matter. This doesn't matter. This doesn't matter. I always align things left just so it's tidy. If you're the type of person who has a really clean house, your cabinets are organized and canned food is, lined up accurately and stuff, fine. I'll align everything the same. I like to align everything left. This matters, whether it's nominal, ordinal, or scale. You're going to have to code for this if you're creating your own database. If you're using a database from someone else, they've probably already coded all of this stuff. Now, the data view, all you have to do is click on it at the bottom. It's always there. You click on variable view or you click on data view. Now we have like subject number, one of the whatever. Age, this person is 19. Subject 1 is 19. Subject 2 is 20. Subject 3, we don't have an age for. Subject 4 is 20. We don't have an age for subject 10. You get the idea. Race is going to be coded in the variable view. And I noticed this one. I didn't do the coding. This was actually a collection of former students put this one together, of my former students in this class. Multiple came together, and I saw Caucasian. If you look back here, Caucasian is such a weird term because, like, I'm not Caucasian. I'm not from the Caucasus. I'm not from Azerbaijan or Armenia or Georgia or and so what Caucasian actually means is not like white person. But let's add some syllables to white person. But however you want to code these things, we all know what Caucasian implies, in most, questionnaires.
I have a quick question.
Yeah, go ahead.
When you put the percent, like the frequency the variable, the frequencies basically,
Mm-hmm.
when you put that in your table, can you use the valid percent? Like, do you have to use a frequency that all the tests,
Valid
like
percent.
everybody tested
Yeah.
in? Like,
I,
if you have 81 people out of the 110 or whatever, can you use that percent?
yeah. I always use the valid percent.
Okay,
I
but
don't
I
use the.
mean, if for example, I put, do you have a job on my
Mhm.
table, and like I think, oh, that's a bad example. They were all tested there, but let me see, like the anxiety question, for example. If not everybody tested in it, do you have to signify somewhere on your table that like
No,
only a certain amount of people
not
did?
for your table one. There are spots in the results section where you can comment on, not everybody was tested for this particular thing, or perhaps a limitation section if that's where it belongs, where you can say, well, only 40% of the people answered this question, and so there are assumptions of, what would be representative sampling sort of fall within that, under that umbrella of the type of person who doesn't answer this question may be sensitive by the answer they give. Now, let's say you're doing a questionnaire. Somebody I know is doing questionnaires on illegal ergogenic aid use. So, steroids, or if you're looking at beta adrenergic agonists, or something that's going to be like a fat loss accelerator, or a muscle, you know acquisition, supplement, but something that's illegal. People don't answer that question if they're taking steroids. Most people don't. It's the equivalent of asking people, do you
Do you do
have
drugs?
do you do drugs, or like, are you a retired child pornographer? People aren't going to say yes if that's true. And if for some reason people are just as sensitive about drug use as they are, heinous crimes and like steroid use or something. People are comparably reluctant to answer those questions. But when you see, like, we have a 30% response rate in this question, you assume the 70% of people that you're asking are probably more likely to be using drugs, or to have some illicit, substance use or whatever it is, kind of undignified background. And so there's room for commentary in people who don't answer the question, but don't put it in your table one. In the results section or
Okay.
in a limitation section is the ideal spot to put that information, saying, well, not everybody answered this question. And so our analyses take it with a grain of at least salt, if not, a grain of hash or whatever, a grain of something stronger than
So
salt.
just to clarify,
Pardon?
table 1, you can just use the valid percent, right?
Valid
Just to
percent.
clarify.
If you've already done table one and used a regular percent, totally fine, right? But for the
Okay.
future, I like to use valid percent there because it gives more information. Um,
Okay, thank you.
Yeah. So again, data view, variable view, just know the difference there. Analyzing, you always use the analysis bar when you go to analyze. Now transform, if you're going to compute variables, data, if you're going to sort variables. Most of this stuff you're not going to use. Window, maybe if you want the syntax bar, but we're never going to do something like that for this class. Analyze is really the only thing we're doing for this class, is you click on analyze, and then frequencies and descriptives, you just go to that descriptives statistic, that little line. Frequencies, that's how you get the percentages, right? The percent, the valid percent, stuff like that. Descriptives, that's how you get the means and standard deviations. And that's where, so the means and standard deviations right here, those are the descriptives, and you're using scale data, the ones with the little ruler, to get these. So it's a bunch of continuous stuff, age, GPA, stuff like that. So the descriptives box, if you have an old SPSS, it might look like this. If you have a new SPSS, it's going to look like this. But just put in the scale ones. Now there's some. This isn't from one of my data sets. This is just an image of somebody else's, because I don't have an old SPSS. But education level. So this would be an ordinal variable, and there's potential cases where you could use ordinal in the descriptives. Maybe okay, fine. But for the most part, what you're going to do is these scale variables, a bunch of continuous data. That's what you put over into the variables thing, and you hit OK. As soon as they're there, you get all of these. And then again, for the percentages, for the total sample, this is only total sample. This is not for subsamples, men versus women, or basketball versus baseball, or some country versus another country, or whatever your subsamples are. If you're looking at salary and education and stuff of physician's assistants versus physical therapists, or whatever subsamples, fine. That's different, right? This is the total sample. And to get these percentages, you're going to do the frequencies. Again, you have old SPSS, you might have a box that looks like this. New SPSS, you're going to have a box that looks like this. And you just put in the binary or any type of categorical variable. If you have ordinal, that's fine. You can put ordinal over here, whatever it is. And it's like, again, I didn't code this one, but minority classification as ordinal, I don't understand why that one would be coded that way, as opposed to simply nominal, which is, gender over here is nominal. And so then you have your entire, once you do your frequencies, the percentages, just percentages, no standard deviations on percentages. You have your total sample, the descriptive characteristics of your total sample. Now we move on to the subsample comparisons, in this case, men versus women. And so to do your continuous variables, independent samples t-test, because men are independent from women. You don't, it's not like men as they're men and then they switch to women, and what are they? That would be a paired samples t-test, but that would be a rare experiment where you see that. And so independent samples, is where you would do those studies. And remember these t-tests, William Seeley Gossett, this is our guy, know his name. He's one of these yeah, major names in statistics. That he appears in a lot of these historical, background of modern statistics. This is a major figure. The student's t-test, right? He was a Guinness employee and he published under the name of Student. And as that story goes, he was Guinness employees were not allowed to publish, to betray their trade secrets. So you get a t-value, and all you need to know for the test, you don't need to know how it's calculated, right? Have an idea where you can always look this up. You can go in the future, you can look it up to know what it means. But as long as you have just some concept of what this means, it's a signal to noise. And you know the signal is a difference in means. Good enough. That's as much information as you're going to be held accountable for this class is t-value, signal to noise. And the larger the signal, the smaller the noise, the more confident you are that there's a difference between groups. So group one, let's say it's men versus group two, women, wonderful. The difference in means, that is going to be your signal. And the noise, the scatter, the variance, how untrustworthy. I mean, this is what it's the standard deviations. This would be sample one. This would be the men, right? Standard deviation squared over the sample size, right? How many men? And this is your second sample. So this would be the formula for noise, signal to noise. You don't need to calculate this. You don't need to recognize this, but knowing the basics of what this is. So question, just wanted to make sure I did this right. Totals, standard deviation and mean are found in the descriptive tests. Yes, that is correct. So for the total sample, now this isn't the population. The population is everybody. The population is like the world over, right? Your sample is the people that you investigated, the people you enrolled, the people you measured, the people you're reporting on. That's your sample. And you sample from a larger population. The population doesn't have to be 8 billion people. The population can be Pacific students, or the population can be Central Valley residents or Central Valley college students or whatever. That can be a specific population, and you have sampled from it. So it depends who you're trying to generalize to, who you're trying to, sort of relativize your findings. Who does this apply to? That's your population. Football players, that's a population. Youth football players, that's a population. Your sample goes in the first column of your actual results of table one. The first column is the names of your variables. When do you use population standard deviation? Population standard deviation, if you test everybody in the population, we're not doing that. We're using sample standard deviation for this class, and I'm not gonna ask that on the test. So that gets a little bit. I just want to introduce mathematical concepts so you have some exposure to what these things are. But yeah, I'm not going to ask that level of detail on the test of, what's the difference between sample standard deviation and population standard deviation. But we're using samples in this class. We're not measuring entire populations. We're taking samples of a population and making inferences about the larger population. Inferential statistics. We're making these claims about the larger population from the sample that we have. So if you test 100 people and the larger population of students who play sports or play video games or play whatever, let's say it's like 1,000 students do that, and you test 100 of them, you have 10% of the population. But we're looking at samples is what we're looking at this class to make inferences about the population. The stats you gave us on student info was UOP students, right? Just curious for the title. Yes. Those stats, those databases. Now, the table one I keep showing is just invented numbers. The table one in these slides is just numbers I have made up. But the database, the outputs, the SPSS outputs that I use are all real. The SPSS outputs you see on the screen, whether it's test results, whether it is GPA stuff, those SPSS outputs are real. And if it's about students, it's about Pacific students. So that should, I hope, answer that question. And so now when you're comparing means, when you're doing subsample comparisons, right? You go compare means, and you would use paired samples t-tests if you're testing the same people twice. Let's test them at pre-test and post-test. Let's test them. Do people like chocolate ice cream, and how much do they like vanilla ice cream? You test people twice, the same people tested twice. That's paired samples t-test. Different groups, right? If you have everybody tests vanilla ice cream, and it's elderly folks and it's babies, and who likes vanilla ice cream more, whatever. Now that's an independent samples t-test. And so if you're comparing subsamples, it's always independent samples t-tests, men versus women, athletes versus non-athletes, Greek versus, Cameroonian, or whatever. You get the idea. So these are real statistics. As I said, all of the SPSS outputs that I put up in our slideshows, these are real outputs. And now this isn't Pacific students. These are some from San Francisco, some from New York. I mean, these are sort of all over the place of people who are tested on Proteus and power, male versus female, means and standard deviation. So I did a t-test on Proteus output on a huge database, right? So there's however many people, 900 and whatever people. And so males and females are more males than females, and the average power in men is 156.1 plus or minus 96.1. The average power in women in this particular exercise, it is a bench press. This is a two-hand bench press, not on an actual bench, but using Proteus, right? So if you've seen that equipment. And so the female is 122.4 plus or minus 54.6. And so the range of motion, the consistency, just curious, what are these measured in? Yeah, watts. Watts. And so sometimes you'll see acceleration or explosiveness or something. So there's maybe a watts per second or so, but we're looking at watts. And the next box, so there are two different boxes when you do an independent samples t-test, right? There's the first box. Now, some of you have already done this. There's the first box, which is going to give you the means and standard deviations of the subsamples, means and standard deviations of male, means and standard deviations of females, and each of the different variables you're looking at. And then in the next box, the next output so no units in the table. That's another question. Do put units in the table, but not in the column that has the data. Put units in the column that has the variables. So I'll show you what I mean as soon as I pull that table 1 back up. But the second box that you're going to see, the second output, and again, this can look different depending on your version of SPSS, or especially if you're using Stata or R or something to do your statistics, these boxes are going to look really different. This is the SPSS 26. That's what I'm using. I just ran these analyses this morning. These tests were done in July of 2020. So these are relatively recent tests from sort of across the US. And what we see is Levine's test for equality of variances. This isn't the p-value report in your table 1. This is over here. Now, this just tells you if you're meeting one of the assumptions of a t-test. Are you meeting the assumption of homoscedasticity or equality of variances? You know what variance is, this measurement of scatter. I think it was in the last slideshow, maybe the one before, where I did the math of how you calculate variance, and then from that, how you calculate standard deviation. So you don't need to do that math, but just the idea of what variance is. This is a mathematical calculation of the spread. What does the spread of data look like? How sort of distributed around that mean are the data, stuff like that. That's what variance is telling you. And are men and women, do they have similar variances? The answer for power is no, they don't. Now, so you would report, equality of variance is not assumed. And so you would report this p-value, but you'd have to report the limitation of Levine's test, that assumption is not met, or homoscedasticity, that assumption is not met, because that's a limitation you'd want to report. And then you report the lower p-value. In this case, it's the same p-value. But this column is the p-value that gets reported in your table 1 or reported in your results section. If your primary statistical analysis is going to be a t-test, this is the column you're reporting. Now, range of motion, you do meet that assumption, you report the top one, there is a difference between men and women in range of motion in a bench press, probably because the men tested are taller, they have longer limb lengths, right? And so they're moving the Proteus, what would be a bar, they're moving it farther, right? And so the range of motion is going to be bigger. But the variance is similar, right? The scatter, the sort of bell curve type of distribution of data, similar between men and women. Same thing with consistency. In serial repetitions, you don't just do one repetition, you do a bunch of repetitions. And the consistency of range of motion and bar path in three-dimensional space is similar between men and women. Men and women replicate repetition patterns in a similar way, but there is no significant difference between consistency of men and women. They are replicating biomechanical movements with comparable similarity, the two. But range of motion, variance is comparable between men and women, but the actual bar path, the length of motion is different. So that's the stuff you report. This tells you which one of these to report and whether you meet the assumption of homoscedasticity. If this is significant, less than 0.05, we have an arbitrary line here, less than 0.05, use the bottom one, use the bottom number, and report that you did not meet that assumption. Here, you use the top number and say, we did meet the assumption of homoscedasticity. And often you don't need to say you met the assumption. That assumption is, if you're reporting statistics, you're giving the impression that you met the assumptions. If you don't meet the assumptions, you have to report that as sort of a limitation. You can report it right below your table one. Again, William Seeley Gossett and his Guinness stuff. That's how we're getting all of this. Now, the earlier question about units in the table. Age in years, BMI, kilograms per meter squared, GPA, nightly sleep in hours, employment in percentage, weekly work in hours. This is where you can report it over here. It just gets a little bit sloppier. Starts to get more cluttered. If you're reporting it 3 times versus reporting it once, this is a better, more aesthetic place to report it. But as long as it gets reported, you can do it however you want, but just consider the ethics of it. Is equality of variance isn't assumed, we should write that under the table? Yes. So if equality of variance, if you don't meet that assumption, what I always do, I always have this little a legend or just explanatory paragraph in a tiny little font beneath the table, little asterisk or something that says equality of variance or homoscedasticity, whatever you want to call it, was not met for X particular variable. For, let's say it was GPA, equality of variances were not met for GPA. Just let everybody know, be informative, don't keep secrets, right? If there's a limitation, be open about it. That means your data are better. If you are sort of concealing things, I hate secrets, right? I hate when things are concealed. And even if it weakens my position, if it weakens my argument, I mean, politics and emotions, people are so secretive in life. And when it weakens their position, I mean, if you look on Facebook or Instagram or something, everybody appears to be having the most wonderful life, and here's me at a beach, and here's me at the museum, and here's me at the concert. Like, I don't think that's what your life is like. I think your life is like sitting around watching reruns, like bad reruns for the 6th time. But every picture of you is some exciting thing, and like, now I'm at Burning Man and my pupils are huge or whatever. And so we misrepresent ourselves in daily life to a ludicrous degree. In statistical life, in mathematical life, in scientific life, at least try to be honest there, where we can report every limitation, report every sort of, if you do something sleazy with your data, post it, right? But say how many different analyses you ran to do this, and what happens when you control for other variables, and what assumptions weren't met. Just put that in there so people know this, how reliable or how valid your finding is. I think you just summed up our generation. I think it's humanity. It would be every generation. If all of this, I mean, I remember the age of the internet when it was bulletin board systems and people were playing text games, and I was playing text games. And so I think I would be susceptible. Our grandparents would be susceptible to the same tweeting and Instagramming, I don't know if there's a verb for that, as everybody who's currently 12 years old, if we had those opportunities and exposures. But back to stats, but this idea of honesty, we want to be as honest as possible. not to the point where it's just cluttered with limitations that don't even matter. But if there's a limitation that is relevant, if there's a limitation that is of some consequence in how seriously we take our findings, or how much confidence we should be bestowing on this result, just be honest with the limitations. The equivalent of posting a picture of yourself, drooling into your pillow. I mean, those are the posts you want to have as well in math. I'm not saying go be um, masochistic in your public image, but I hope that makes sense. That this idea of this sort of tangential idea into social networking is framing what I'm trying to say about honesty, and not creating a false impression of this wonderful finding, right? Not this false, because it's what. Let's a moment. Just forgive me the moment of a tangent. Watch people on Facebook or Instagram or something when they're talking about how wonderful their relationship is. If they're married, set the kitchen timer and that divorce is coming soon. If it's just like a normal relationship and they're like, I have the most loving boyfriend or girlfriend and I've never been happier and whatever, that person's probably crying themselves to sleep at night. So when you look at it, when people declare something too loudly, it's sort of a window into their soul where they're kind of telegraphing the opposite of what it is. And statisticians do the same thing. Scientists and physiologists and we all are susceptible to this deficit of human functioning and human reasoning, and we just want to be as honest as possible. And honesty is tough. Honesty is one of the hardest things there is in life. Do these jeans make me look fat? Actually, they're not flattering to your form. That's not a sentence that people are hoping to hear. We expect dishonesty as social etiquette. Don't do it in statistics. Just be as honest and direct as possible, and the world will profit from it. Okay, so if we're going to do a chi-squared, right? Remember, that's a chi-squared is descriptive statistics crosstabs. Now we're going to compare percentages. Crosstabs are going to compare percentages. Do we expect between males and females political party to be the same, right? That would be a chi-squared analysis. So you pull up that crosstabs. And remember, this is old class data where it's males and females and whether, yes or no, whether they know their astrological sign. You want to click on statistics, click on that little button, and you'll get the chi-squared. Click on that. Now we have a chi-squared, and we'll phi or phi and Kramer's V. You can do that too. Looking at correlations. And so again, like phi is probably the real, if you're looking at Greek, or you're reading the Da Vinci Code or something, and watching the movie or something, and that pronunciation is phi. Phi is a common pronunciation. That's fine. Correlation between two dichotomous variables, yes or no's, right? So that's all that is. Now you get to a Kramer's V, and what that's going to be is this correlation, association, relationship, however you want to explain it, between categorical variables that are not 2 by 2, right? It's not males and females and student or non-student, right? So it would be like males and females in political party where there's Republicans, Democrats, and independents or something like that. That's Kramer's V. Now, we're not doing Kramer's V and phi in this class, but that's a common one that people will look at. And then you want to click on cell over here and just put on the column, and then continue, and then hit OK. And then you're going to get your findings. Now, if it's an older SPSS, it might look like this. So Kramer's V would be categorical. Categorical, yeah, so the Kramer's V, if you're going to have these categorical associations, yes. Now, there's very few students do I work with about the analyses we're covering in this class: descriptives, frequencies, and I promise I'll get to the rest of the comment box in a sec. Descriptives, frequencies, t-tests, both independent sample and paired sample, chi-squared, and then we move into regression, and we do linear regression, logistic regression, and I talk about, but I don't make you run, I talk about negative binomial or Poisson regression. And then after that, we do repeated measures ANOVA, which is like ANOVAs are fancy t-tests where you're doing a bunch of comparisons all at once. It's not just 2 subsamples, right? You have like 6 subsamples or something like that. Or people are tested serially. If you're going to use repeated measures, ANOVA, people are tested at baseline in 6 weeks and 12 weeks and 18 weeks, something like that. The rest of the statistics, Nathaniel is probably the only student I've ever worked with to teach additional statistics beyond this, because he and I do research collaborations outside of class, and I will sometimes move into further statistical models, but they're not very common. And so we can talk about all of those. And so ANOVA could be like race, that is true. So there's, if you're looking at multiple races, now we're not doing an independent samples t-test, we're doing an ANOVA. And so a one-way ANOVA is what it would be called. We have like white and black and Asian and Pacific Islander, whatever it is. We look at all these different groups. That's not comparing two groups. You can compare two groups. You can say like, I don't know, white and black or something, and that would be an independent samples t-test. But if you have multiple groups, that's not two, that's not an independent samples t-test, that's an ANOVA. That would be a one-way ANOVA. And so the rest of the statistics, let's talk about those. If we're going to get into research collaborations and publications outside of class, there may be things that we talk about, additional statistical models that are appropriate to answer other questions, but we don't encounter those scenarios, those questions very often. And the scenarios that we encounter like 97% of the time, 98 maybe percent of the time, the vast majority of statistical questions are going to be answered with the models we talk about in this class. There are exceptions. There are some other types of research questions, inter-rater reliability or something that can be answered with different statistics, and we can talk about those another time. So again, crosstabs. If this was me taking someone else's, because this isn't my version of SPSS, I would put gender. I would call gender sex unless it's like the sociological version of gender. So sex would be the biological version. And so if it's males, females, but I would put it here, and I would put what you're comparing up top. Who cares how you do it? You're still going to get the same p-value. You're going to get the same results. It's just easier to go to the cells and put column and get the appropriate statistic that way. And then what you would do is, again, chi-squared. And if you feel like doing phi and Kramer's V, that's totally fine. We're not going to use those in this class. Now, that finishes our table one, right? These are percentages, subsample percentage comparisons, and the associated p-value that comes with it. So the correlations, this is the questions at the start of class with the bivariate correlations, bivariable correlation. So two variables, do they move together? Are they correlated? Do these two variables, do they correspond? Do they associate? However you want to explain this, are these two variables related? Pretty much everything is related to everything to some degree, but there's strong and weak correlations. Now, you go to analyze, so for your lab, you go to analyze, correlate, bivariate. Ignore these three, right? Bivariate, click on that one, and then just drag everything over that you want to correlate. Binary variables, continuous variables, just drag everything over. And it's going to give you the Pearson correlation coefficient, right? A Pearson correlation coefficient. Now, these correlations, if this is technically the Pearson correlation coefficient is going to be continuous to continuous. These numbers are where it gets confusing for all of us. Yeah, I haven't really talked about this yet. I think I sped through it with such haste in maybe the last lecture or something. That wouldn't expect anyone to be able to read this table. You get a huge table. Okay, however many variables, you can either just double click on the variables or click on them or drag them over, whatever. You just throw all the variables you want to look at. I love doing this analysis because once I've built a table one, I want to know what's in the data. What variables are associating with what other variables? And I can start to get, like if you're sort of blind, I get a database, and the first analysis I do after characterizing my sample, after exactly those analyses we just did. After I build a table one, the first thing I do with any database I get, whether it's 100 people, 1,000 people, I build a table one. And then the first analysis I'm going to do is bivariate correlations. I just throw everything in there. But the first things I'm going to throw in, the first few, are variables I'm interested in. So I might be interested in age, heart rate, systolic and diastolic blood pressure. And you're going to get this massive table. If you've done this and you put in like 50 variables, you're going to have 50 variables going this direction and the same 50 variables going this direction. So obviously age and age is right here, pulse and pulse. So you ignore those boxes. But age, does it associate with heart rate? Yes. As you get older, as age increases, heart rate goes down in this sample. Significant because there's 2,000 subjects. It's actually a very modest effect. Age, does it associate with systolic blood pressure? Significantly, yes. P is less than 0.001. Never say P equals 0, because that's never true. That's not a thing. Right now, P is less than 0.001, that's how you report it. Because you see 0.000, what this means is there's a bunch more zeros or something, and you get to a 1 or a 5 or 0.0002 or something. So technically, what you could say is P is less than 0.00005. Because technically 0.0005 would get rounded up to 0.0001. But who cares? Nobody phrases it that way. In the literature, nobody says P is less than 0.00005. Nobody says that. Everyone just says P is less than 0.001. That's how you phrase it. You never say P equals 0. Don't do that. If you already turned in your table 1 and you said P equals 0, whatever. I haven't said this yet, and that's fine. It's fine for the lab 1. Just don't do it again if you already did it. Or if you haven't turned in your lab yet, correct it. Put in P is less than 0.001. And so all you have to do in the lab is just look for a finding. So here, there's tons of significant findings. You'll see little asterisks, little stars next to anywhere where there's a finding. If there's 1 star, that means it's less than 0.05. Here's one, less than 0.05. So this is age and mean arterial blood pressure. So diastolic matters more than systolic, but it's just a average arterial pressure. Now, or diastolic, you see a single asterisk. That just means it's not less than 0.01, but it is less than 0.05. That's all that little asterisk means. And so it's just a way of identifying strong relationships without having to go one by one and look at the significance and go, okay, that one's strong and that one's weak and that one. And so whenever you see these little asterisks, that's just flagging it. That's just saying, hey, pay attention to me. 2 asterisks, really pay attention to me. But again, p-value does not tell you magnitude of effect. It just tells you confidence. That's all it tells you. Does it signify there's a difference? Not how big the difference is, not how the matters of scale and the magnitude. P doesn't say any of that. P just says, is there a difference? How confident are you? Does it signify? Significance signifies. That's what it means. Significant does not mean colloquially, scientifically. There's no environment or scenario or context or conversation in which significant means large, right? That's not even close to what the word means. It just means, does it signify? Is it a sign, right? A sign, significance, a sign. And that's all it means. Can you touch on the meaning of what an extremely low p-value would mean? So an extremely low p-value, like this. So if this were 0.001, we would say there's a 0.1% chance that we would have observed an effect this big or bigger. In this case, this negative or more negative than that. This extreme or more extreme, of this magnitude or a more extreme magnitude. There is a, in this case, it'd be less than 0.1% chance, right? And move that decimal point a couple of spaces. Less than 0.1% chance that you would have observed an effect size of this magnitude or greater than that if the null hypothesis were true. Now, the null hypothesis in this case is, does age correlate with heart rate, with pulse, right? A little bit. That's a really weak correlation, but with 2,000 subjects, weak correlations signify that there actually is a difference. They are a sign of a difference, even though it's tiny. The effect is tiny. It's not big. That's a tiny, tiny little correlation. And now again, there's different, like a point biserial correlation. This is just going to be like if you have some, binary variable like isn't in here. But if it was like sex, if it's males and females and pulse or something, what gets listed here would be called a point by serial correlation as opposed to a Pearson correlation coefficient. That doesn't matter though. The number, it gets calculated in a way that you would report, and so you don't actually need to know that. But there are different names for what these things would be, the types of correlations that you're seeing in this table. But bivariate correlations, two variables correlated, and a Pearson correlation coefficient is really describing two continuous variables, which are all of these variables are continuous. Temperature, what is somebody's core temperature in a doctor's office? They're not doing like rectal temperatures or anything. They're just like looking at foreheads and ears and maybe a mouth or something. So so there's argument of what core, but temperature, body temperature is associated with age. As people get older, they get colder, right? So everyone moves to Arizona and Southern California and Florida and stuff as they retire. Really significant, but there's like 2,000 subjects, right? So, but in a negative. So as people get older, temperature goes down. Now this doesn't tell you how. It's not like every year temperature goes down by 1/10 of a degree. That's not what this is saying. This is just a correlation coefficient saying the strength of a correlation. Regression is going to tell you, in this case, a linear regression is going to tell you the actual amount with each additional year of age. How many degrees of temperature can we expect to go down? That's a regression. A correlation is just telling you it's in the opposite direction. As you get older, temperature goes down. That's what that negative means. If it's a positive, as you get older, pulse pressure goes up, so your systolic over your diastolic, your with each pulse, right? So the systolic minus diastolic. What numbers are we looking for to consider something a strong correlation? So a strong correlation, good question. First off, let's start with a p-value. Again, anything below 0.1, you can start to observe. And where it's less than 10% chance that you would have observed something this strong or stronger than that, something this big or bigger than that, something this negative or more negative than that. P-value less than 0.1. Now, classic rigidity, p-value less than 0.05, that is significant. Don't call 0.06 significant because the peer review process will reject you. 0.05 to 0.08, people call that a trend, a statistical trend. This is just conventions. You know what p-value means. Who cares what, 0.05000001 is really the same prediction as 0.049999. It's like the same number. It doesn't mean anything different. And yet conventions tell us it does. Now, so you look at p-value, and that's our confidence. The question was about what is a big correlation and a small correlation? It depends on the nature of the interaction. So let's say we're looking at something like we find a drug that cures cancer, cures HIV, cures whatever. You give me a correlation of 0.3 and there's no side effects. That's being published in Science or Nature, New England Journal of Medicine, a correlation of 0.3. And now 0.3 is kind of weak. You get below 0.3 and you're like, this isn't very compelling. This isn't very strong. Correlation, you get into like that 0.5, 0.6, 0.7, and we're looking at much stronger correlations, 0.8, and it's just outrageous. This is really, these two variables really move together, correlation of 0.7, 0.8. Below 0.3, and we're looking a little bit weak. But so the question, it's a really good question. So 0.3 is when you pass the Snicker test. Yeah, to a degree. Now, let's say you find a spurious correlation that says dog owners, yes or no. So it's dog or cat. Let's say people who prefer dogs versus people who prefer cat, binary. So this would technically be a point by serial correlation as opposed to a Pearson correlation coefficient. It's going to be calculated the same. Again, who cares? You're going to get this number that you can report. And IQ. And you take this sample and you see like a correlation coefficient of 0.39 and a p-value of 0.04 or something. I really doubt that there's some IQ relationship with pet preference. Maybe there is, but that wouldn't pass the Snicker test for me, even though there is a correlation and a significance, and both of them fall in that sort of compelling region. You still want to apply some rational scrutiny, not scientific mathematical scrutiny, but some rational scrutiny. So the Snicker test encapsulates more than just what the statistic itself is reporting. So all you have to do for the lab is run a bivariate correlation and then just find a couple things and report them. They don't have to be significant, but you want to report what it actually means. So let's say this is your output. What you'd report is, here's a couple of interesting findings. Diastolic blood pressure tends to increase with heart rate. As heart rate goes up, we see diastolic blood pressure going up. And then put in parentheses, R equals 0.170 semicolon, P is less than 0.001. Is that a profound effect? Well, no, it's a low correlation, but again, with 2,000 subjects, it still signifies that there's a difference because there's just so many. If 1 billion people all sleep an extra 5 seconds when they take some, sleep aid, then it's significant. Oh, you're definitely going to sleep more. Is it relevant? Is it practical? Is it meaningful? Well, no. 5 seconds of sleep is not going to change how exhausted we are the next day. But is it significant? Yeah, absolutely. We're almost like 100% sure. We're like 99.999% sure that you're going to sleep 5 additional seconds. Okay, that's not really helpful. And so what practical meaning is and what statistical meaning are, we have to use a little bit of, just again, going back to the Snicker test of we have to characterize things in a way that's meaningful or considers magnitude and practical applications. But that's all you have to do. So temperature, a body temperature, what is it related to? Well, age. As we get older, temperature tends to decrease. With each additional year, we tend to see body temperature going down. P is less than 0.001. So parentheses, R equals negative 0.111, semicolon, right? The elevated dot in the comma, the like dot floating over the comma. P is less than 0.001. That's what you'd report. You just report a couple of those things and then say, there's if the null hypothesis is true, there's less than a 0.1% chance that we would have observed an effect of this greater greater. And that's it for the lab. That's all you have to do.
Can I ask a question?
Yeah.
So in my bivariate correlations table, I see that with the two variables of how many units are you taking and have you declared a major, I see a Pearson correlation of 0.304 with two asterisks, and the significance is 0.001. So
Okay.
that would be considered, right?
Highly significant, people would say. You get less than 0.01, people start saying highly significant. And but just have integrity and just call it plain old significant. People add these adjectives to these are highly significant and drastic, whatever. They just let the numbers tell me how drastic and impressive and probable this is. And so just call it significant. And just so let the numbers do the heavy lifting. Don't let adjectives do heavy lifting for you in your reporting. But with that one, you would say whatever it was, your two variables are correlated, colon, R equals whatever it was, P equals 0.001, 0.001, end parentheses. Yeah, so that is a strong correlation. Those two variables do move together compellingly.
Okay, thanks.
Yeah. So again, this is what the data are going to look like. If it's just two variables, as one goes up, the other goes up, and it's perfect, that's a 1. You're not going to see ones, really. I mean, this is really strong. This is okay. 0.4, that's okay. Again, you get like below 0.3. It depends on context, just like 0.05 depends on context. And Fisher said as much. He's like, I wouldn't say 0.05 for every experiment and every condition with all variables across the years and across fields and disciplines, or whatever. 0.05 is not law. But 95% confidence is certainly a reasonable threshold for this experiment. And so with 0.05, we same thing with these Pearson correlation coefficients, right? Carl Pearson. The correlation coefficient, the R, right, a little lowercase r. You get below 0.3 and you sort of classically, like, we're getting weak. but it depends on the experiment. It depends on the nature of it. So now remember GIGO, garbage in, garbage out. We're going to get back to what we're going to move into is talking about the next lab. And it's going to be about GIGO, right? It's going to be about analyzing shitty data, and can we get reasonable findings from shitty data? Probably not. I'm not saying always you can never get anything from this. There may be certain types of questions where you can say error rates and types of analyses where you're talking about teaching journals and stuff. Sure, there's certain stuff that can come out of a bunch of garbage that is of value, but in general, GIGO, garbage in, and it's hard to extract anything of value. Now, this gets into a touchy subject, what people today would call trigger, right? I'm being triggered. My heart rate is elevating, and my systolic blood pressure and heart rate are elevating. My age staying the same. What's the correlation doing now? But this is really touchy, especially in Stockton, which Stockton is not immune to school shootings. What put Stockton on the map? It is right down the road. Cleveland Elementary School, right? Patty Purdy, right, is 1989. Just Google this, right? Patrick Purdy, whatever. Did this like sort of horrible school shoot. All these things are horrible, but a particularly gruesome one with like weird shit written all over his guns, like grammatical error. I mean, it's really weird. It's 1989, right? So like Michael Jackson was a huge thing. He comes to Stockton. It was this big deal, and that's right down the road. So Stockton is not immune and probably more susceptible than anywhere to school shootings. Now, what I'm not doing here is taking the emotion, the tragedy, the devastating responses in life. 15 minutes, thanks. The devastation to a family away from all this. The only thing I'm talking about is the results that people are talking about a day after a school shooting. You got the NRA coming out and saying, see, if only teachers had bazookas. And on the other, obviously I'm being sort of, I'm exaggerating. I say that in jest. There's an amount of facetious, the way I'm going to talk about this, I'm sorry if this is like a really emotional subject, but I talk about things in a very, very cold, calculated, scientific, unemotional, unbiased way. And if my tone offends you, I'm apologizing in advance with an amount of sincerity. But opposite that, both ends of political extremes here will get on the news and start saying, see, guns should have been banned so long ago. We shouldn't even have invented the longbow, right? That is a weapon of mass destruction. And so there's one extreme gets on the news and with veins in their foreheads and in their throats, right? Are sort of vehemently declaring their position. And on the other extreme, it's some NRA enthusiast, we'll call an extremist, who is saying, yeah, every single person in America should have 100 million guns and should have, like James Bond weaponry in their garage. So we have these two extremes. Now, what I'm going to talk about is the data. Think garbage in, garbage out here. And I'm probably the most equipped person in the world to talk about this, not because I'm the person who knows the most about it. I've read some. I've read, I don't know, 30 journal articles. I'll show you some of them. Some of them will make an appearance in this slideshow. I'm not the most well-read, the most well-versed. You should not put a gun in my hand. My first two encounters with guns, one I sprained my wrist shooting a tree. I grew up in Oregon. My dad had this big shotgun. I shot it and my wrist never healed. And then the second time I had a gun, I almost shot my foot off because I didn't realize it just automatically keeps shooting. You didn't have to cock it every time. And I adjusted my hand. It went into the ground about a centimeter from my foot. And the next shot ricocheted off of I was in Eastern Oregon, or what does one do but shoot guns at like stop signs? As I ricocheted off of this like industrial freezer from like World War II. And I heard it go shooting by my face. I put the gun down. I said, I'm done with this. Projectiles don't belong in my hand. Now, I don't care if projectiles are in other people's hands. I know my hand is not a very good one to hold a weapon of any variety. People are going to get hurt if it's in my hand, and it's probably going to be me. But that doesn't mean I'm going to legislate against other people and I'm going to abuse statistics to support an invalid position, right? So for me, the reason I am an authority here is I don't give a shit, right? So to me, this whole argument about gun debates, it gets so heated, but to me, it's just as boring as Anna Karenina. The book, I never saw the movie. I used that book as white noise, as a sleep aid for about a year, and I don't think I ever finished it. It was so fucking boring. And whenever anyone starts going into their gun debate and the heat that they bring into this argument, I nod off. I mean, I hope I can get people to come do this in my bedroom to put me to sleep because it's so boring to me. So to me, if we decide projectile weapons, the only projectile we get to use, not even slingshots, the military. Yeah, you're a Marine, you're like a Navy SEAL, you're whatever, and you have to fight wars with water balloons. Fine, I'm sure we'll come up with something. You know, we're countries filled with smart people. We'll come up with a way of, you know, preserving national security with water balloons. I'm sure it's capable. I wouldn't, my heart rate wouldn't change. Opposite that, if some legislation passed that said, all right, everybody, as sort of like a earlier life, you know, bat mitzvah, bar mitzvah kind of equivalent of like you turn 6 and you are given, you go to the grocery store or Walmart and that's what you get, right? Like every 6-year-old in America gets like a 1988 bazooka. Fine, I'm sure we'll come up with a way of managing that. I don't know. I really don't care. So lab 2, what we're doing with lab 2 is trying to be more friendly to statistics, to mathematics, to science than we are to bias, right? People get so biased, so caught up in their cleats, are dug so far into their belief system that they are hostile to evidence and logic and reason and rationality. And lab 2 is an exercise in not conflating values with facts. Every single year I do this lab, I get somebody who can't possibly find, you know, I refuse to find statistical support for something that opposes my values. I will not dignify an idea that throttles my deepest integrity. What would be the most unethical or far from your belief study that I have done? We'll talk about that later. Well, I'm happy to dive into almost any research topic, but publication, I don't necessarily want things attached to my name of disciplines that I would study in. But I'm delighted to be people's statisticians for any experiment. I just don't necessarily want things always attached to my name. I don't want to be a spokesperson for things that are too heated, because then you know, it's an invitation for a hate mail, and I don't want that stress. Anyway, so what you're doing, what you're not doing in this lab is trying to support a belief system. What you are doing in this lab is showing garbage in, garbage out, while learning how to evaluate that with SPSS, how to evaluate whether data are permissive of running your findings, whether data lend themselves to accurate analysis. So this is how to use SPSS, how to appraise quality, how to see if you're rifling through some trash, or if you're working with data that actually can elicit compelling findings. And what better thing to analyze than a hot topic that gets hotter every time there's a new school shooting? And again, what I'm not doing is saying this is unimportant. What I'm not doing is saying there's no such thing as emotional hardship or you know, gun violence ripping families apart and sort of destroying quality of life. I'm not saying that. What I'm saying is the data are bad, right? Whenever people are making claims, they come on the news immediately after a school shooting and are livid, and they're saying, if only this and that and this, look at these statistics. Those statistics are flawed, and they don't actually say, they don't support what the person is saying. So the way that these questions are answered, all of these gun statistics are 100% epidemiology, right? There's nothing but epidemiology here. You're not doing randomized controlled trials, right? Where you're like, okay, we're going to issue guns to this household, and we're going to keep guns away from this household, and we're going to put them in scenarios that might elicit, homicide. You're not going to run a randomized controlled trial, so you do epidemiology. So reflect on the findings of epidemiology, right? Now, whether it is a vitamin, or it is a pharmacological intervention, right? It's estrogen, replacement or something. All of these, they tend to turn out hilariously false. Often, not always, but often enough, the opposite of the truth. Now, not even the majority of the time are they the opposite of the truth. And usually it's just like, that's a spurious finding because you didn't consider the type of people who. And so a lot of these epidemiological findings, what we wind up with in the end is an amount of delusional optimism goes into their acceptance, right? Rationality goes into their rejection. So it's slender odds that it's going to be true, right? It's not just like slim, like a person is lean odds, right? It's slender, like osteoporosis on a Halloween skeleton. That's how slim the odds of these epidemiological findings, especially of this nature, are to be true. You can almost assume the opposite is going to be true, or there's no finding whatsoever. And so what you're going to do in the lab, there are 3 possible findings. Okay, you're going to take a real database. This is the same database that has been used again and again and again in the media, in what gets published. People are using the same database that will be uploaded, if it's not already, on SPSS. And you have to use that same database, the exact same one, to come up with 3 different findings. And you're going to use regression to do it. Or you can use correlations, you can use whatever you're learning, but I use regressions. It's more compelling. Guns reduce crime. So guns are good. We just need to arm everybody, right? Put guns in the hands of 6-year-olds, put assault rifles in, grandmother's hands, and every teacher should, be able to kill the Witcher. Fine. Okay. Guns reduce crime. Guns promote crime. You have to find that too. Same database, same variables, same numbers, same everything. Run the analysis in a slightly different way to show that guns promote crime. And then you have to show that guns have no effect on crime. That's the easiest one. And both of these are relatively easy too. I can usually give me a brand new database, and I can do this in 5 minutes with pretty much any database. I can come up with opposing findings for anything, but statistically support at least 2 of the 3. I really don't care if you do this one because it's so easy, but you certainly at least these 2 opposing ones. This may sound stupid, but how do you do this with the exact same database? I'll talk about it. I promise I'm going to talk about that. So let's just talk a little about the history, and then probably next lecture, I'll talk about the actual methods. So on Friday, I'll talk about the methods of doing this. But so I lived in Storrs, Connecticut when the Sandy Hook shooting happened, and Storrs is up here. So I'm northeast of Newton, which Newtown, right? Which I'm pretty sure it's pronounced Newtown, not Newton, like it's a fig. But so I lived in Storrs, which is up here, but it was all over the news. And my friends, 5 minutes, thanks. My friends back in Salem, Oregon, where I was from, and some friends from Stockton. I lived here before too, before I moved out to the East Coast. And everyone's writing me and telling me how, oh, I'm so sorry for your loss. I didn't know anybody. There's the losses belong to the people over here, not to me. I didn't know anybody. And so there's devastation over here, but up in Storrs, I've never heard of any of these people. But what you look at is immediately afterward, Face the Nation, right? This is 2 days later. So December 14th to December 16th, 2 days later, people go on the news and they start making all these claims, right? So every day in our country, 32 people are murdered by guns. So while violence rates might be going down, gun violence rates are not. But you look this up. I always look up this stuff because I'm like, this is interesting. 32, is that not going down? I have no idea what 32 means. So where'd you get that number from? Is that valid? And what was it the year before? And what was it the year before? So I go look stuff up, right? So according to a footnote in this, there's, comes from this particular database, the CDC database, and I went and analyzed it myself, right? So there's 33 and a third. They were actually, they could have increased their number a little bit and been more accurate. But so the thing they're saying though is that gun related homicide rates, that this is going up. But like it was the lowest on record when they were making this claim. 1993 was horrible. 2010, not that bad, right? It's like half of what it used to be per day. And so some of these claims, people just say like 32, gun violence and gun homicides, these are going way up. Like, just look, you verify things, and what's said on the news is so commonly false. People just don't think that they're going to encounter somebody like me who's going to go, let me go look up what you're saying. Nope, you're an idiot, right? Validate things. Don't just repeat stuff. Go validate it. Look it up. It takes time, and I don't validate everything, but I don't repeat what I don't validate. And so looking at where did the source come from? Well, if it's from the CDC, um, they're looking at justifiable homicides, or someone's coming at you and in self-defense or something. So that's not like murder, right? It's coming from the FDI, from the FBI. This is voluntary reporting. It's going to be underestimating. So maybe you have an overestimation up here, you have an underestimation down here. So it depends where this stuff is coming from. But then you start seeing the really vehement ones. The sort of is maybe a little bit too much body fat to have the vein in his forehead, but again, December 14th to December 16th. The facts are that every time guns have been allowed, concealed carry gun laws have been allowed, the crime rate has gone down. Okay, we start barking this. What we need to do is arm the teachers in Newtown, right? Okay, this is me chiming in. What outliers are you ejecting from your analyses, and what reason, right? Is it a justifiable explanation for how you're ejecting your outliers? You're ignoring particular districts, and what inclusionary, exclusionary criteria are you enforcing to make that statement true? Because the statement actually isn't true. But you can analyze anything. You can take any database and analyze it in such a way that it becomes true. And almost all of these analyses come from this guy, John Lott Jr. He's very smart. He looks dangerous, but he's actually a very smart guy. This economist with he's stuck with UCLA, but his PhD from UCLA in economics, and he talks about violence coinciding with concealed handgun permits issued, coinciding. Right now, we know that cliche of correlation and causation, right? Of just because something has a correlation or it coincides does not mean causality is present. And so he sort of talks about this from between 1977 and 1995, starts talking about the history of this stuff. And this is John Lott Jr. right here. This is an article that predates some of his books. But remember this: Age of Miss America and murders by steam and vapors and hot things. We don't think Miss America is going around blasting people in furnaces, right? But this is correlated, right? This has the same coinciding that John Lott was talking about. And here's me. I did this analysis this morning. I'm predicting sex. I'm predicting whether someone is male or female. This is a logistic regression using age, height, weight, and power. They are all significant predictors of whether somebody is male or whether somebody is female. Now we'll talk about logistic regression soon, but this is a ridiculous analysis. Sex is predicting whether somebody has a higher power output or how tall somebody is, right? Those chromosomes are predicting in the opposite order. Oh, I grew taller. That's going to make me a male. Come on, right? And so you have to consider that sometimes gun laws are enacted because of the violence. And then when you look at the violence, doesn't go away on day one. And so it depends how you're analyzing these things and in which direction. Now, getting into some people who are looking at these right to carry permits, the National Academies of Sciences, Engineering, and Medicine. Like, what, these right to carry, there is no link here. You really have to enforce weird things to elicit this effect. This isn't just a crude analysis that is immune to manipulation. Earlier in the semester, half a dozen lectures ago or something, I said, statistics are not like rocks. They don't exist in nature. They're handheld human interventions. They are not immune to bias. The more we handle statistics, right? This is an intervention. The more we handle these things, is, the more likely we are to bias our outcomes. And handling gun data, man, do people handle this stuff and enforce things differently. So let's take my original, another analysis I did this morning. Let's take an original the thought of what predicts sex. Ooh, as you get older, you're more likely to be female. Significant. P is less than 0.001. Okay, this is ludicrous, right? We know that as people get older, they don't become females. That's what this statistical analysis is saying. Now, here, all we have to do is include sport. What sport do these people play? And age no longer matters. Let's hold sport constant among baseball players, among hockey players, among basketball players. Let's hold sport constant that these people are playing and look at the exact same variables. Age doesn't matter. So you can manipulate these things. You can manipulate these variables in a way to elicit the finding that you want. All right, it is 1:48. We are done with class for the day. To whatever day, Friday, in a couple of days, we'll talk about the analyses that you run. I'll finish up this little bit, and then we'll get into which analyses you'll run for lab 2 with a little bit more framework and context and sort of scenario scene setting, and then we'll just leap into regressions. So, all right, let's get out of here. I'll see you guys in a couple days.
Oh, just to be clear, we can email you with any questions about our project still, right?
Yes, you can. Oh, and send me
Or our lab. I mean, sorry.
oh, the lab. Yeah, but get in touch with Nathaniel first, and then if you
Oh,
have
I already
additional, pardon?
Oh, sorry, not wrong person. No, I was thinking about my partner. That's
Oh,
different.
okay. But also let me know. I have the idea of what your topic is, what your poster, what your project is. But let me know, research partner. You know what your group, if you have a group, how big it is. Just let me know that stuff, and then whenever it's, you don't have to let me know for a while, but let me know on if you have a lab question, or you can send it to Nathaniel. Nathaniel's grading the lab, so it might be better for him to receive those questions directly because he's the one who's going to be assigning points. And so to get an answer that is more precise for what he's looking for, but I'm happy to answer those questions as well.
Okay, thank you.
All right, I'll see everyone.